We have seen that a wide variety of energy models exist. They are different in geographical resolution, geographical scope, time scope, different sectors of the energy chain they are able to consider. How to choose the right model then? The most important question to keep in mind when looking for the right model is what is my scope? That directly translates in what do I want to model and what answers am I looking for? Are you performing an analysis at local or national level? Is your goal that of sizing a rural mini-grid, planning the evolution of the energy system of a country through the energy transition, or designing a strategy for reaching universal access to electricity in the sub-Saharan region? All these questions allow me to identify the correct model or understand how to build a new model that satisfies my needs. In the following slides, we will see an overview of some widely adopted energy models and some applications to understand their potential. In this example, we adopted the open source software Calliope to perform the analysis of a future smart energy district outside Milan. The study in particular investigated the synergies between residential buildings and commercial buildings' energy needs in terms of heating and cooling services. Through the software, it has been possible to model the presence of photovoltaic panels on the top of the buildings, the connection to the national electricity grid, and a system of heat pumps for heating and cooling of spaces and for domestic hot water provision in the residential building that used, as a thermal sink, a common water body. In this way, it has been possible to derive the economical and emissions-related advantages of this integrated system with respect to a traditional system. In this second example, we make use of two open source tools, RAMP and MicrogridSpy, to first estimate the electrical load demand of a rural community not served by the national electricity grid, and the possible evolution through time of this demand in different scenarios. Secondly, these load profiles are used as input for a mini-grid sizing tool capable of considering the evolving load of a system and to optimize stochastically over the different scenarios. The result is the sizing of PV panels, battery pack, and backup diesel generator of a system that is capable of satisfying all the demand scenarios at the minimum cost. With the third example, we move at national level energy strategy analysis. In this case, we adopted again the modeling framework Calliope, this time to the Italian energy system, and we investigated the effect of 100% adoption of induction cooking stoves in Italian households overnight, substituting the existing fleet of gas cooking stoves. Interestingly, the results suggest that, given the Italian electricity mix of 2019, the massive introduction of induction stoves would cause a surge in the electricity demand during the evening hours that would be covered by natural gas-fired power plants, resulting in an overall, even if slight, increase in carbon emissions by the system. In fact, the amount of gas burned to cover the additional electricity demand is higher than the amount of gas not burned for cooking uses. This does not mean that induction stoves increase emissions in general, but the result depends on the electricity mix of the country, calling for detailed analysis like the one presented. Moving to a dynamic analysis, thanks to osmosis, it's possible to optimize the evolution of energy systems. Osmosis is, in fact, a dynamic model, and is clear in the example showed here for the Ethiopian National Electricity System Planning. Providing exogenously the evolving energy demand of the country, according to the forecasts and national pledges, the tool provides the cost-optimal solution for two decision variables: capacity installed for every power production technology and energy produced from installed technology. It is as well possible to compare different scenarios, applying, for example, different policies or constraints. Finally, as a last example of another category of models, is represented by ONSET. It belongs to the category of geospatial electrification models. This category of models works over a geographical information systems, or GIS, to provide snapshots of least-cost technological solutions for providing access to electricity to rural community not connected to the national grid. In the example shown here, we can see the case of Bolivia, and each colored point represents a different technology, different kinds of mini-grids, standalone systems, or connection to the main grid.